Hello, and welcome to the presentation for our paper, NuTrea, Neural Research for Context-Guided Multi-Op KGQA. The multi-op KGQA, or Knowledge Graph Question Answering, is a question answering task that works on knowledge graphs. When given a natural language question, the objective of the task is to query a knowledge graph to retrieve the set of nodes that answer the given question. And generally, a subgraph is extracted from the entire knowledge graph for each question, and the seed nodes are assumed to be given, which refer to the nodes that represent the key subjects in the question text. And recent works attempt to approach this task as a path-searching algorithm that tries to learn the path from the seed nodes towards the answer nodes by aligning it to the question. But in searching the path towards the answer nodes, we here identify two important challenges. The first challenge is that the knowledge graphs contain proper noun entities, which can be difficult to convert to meaningful embedding vectors. And the node entities are often encrypted as seen in the example, making it even harder to encode. Another challenge is that the recent BFS-style search mechanism tends to accumulate past-oriented information onto the nodes as the model sequentially expands the search area, making the search difficult and inefficient. Hence, we present solutions for each identified challenge. First of all, to handle the problem of uninformative nodes, we propose relation frequency inverse entity frequency node embeddings, or RFIEF, which was inspired by the TF-IDF method in NLP. And because the node embeddings are difficult to initialize, several previous works resolved this by initializing the node as the average over the incident edge embeddings. We enhance this idea by reweighting the edge embeddings to better characterize the node entity. Technically, we compute two matrices. First of all, the RF matrix gathers local information by counting for each node V the occurrence of the edge type R incident to V. So in the example on the right, it will be something like 1 for deliver speech and 2 for the edge type related to. Then we compute the IEF matrix, which is the log of the inverse the count of nodes that have edge type R in its incident edge set. So these values are computed over all the knowledge subgraphs in the training dataset, incorporating the global statistic of the graph. Then these two matrices are multiplied as follows, resulting in a weight matrix for all nodes in V subscript Q over the relation types in R. Then, similar to the TF-IDS mechanism of characterizing text, the globally frequent edge types will be suppressed while emphasizing the globally rare and locally frequent edge types. Next, we propose NuTrea, which improves the past-oriented information accumulation in previous methods. So before the actual NuTrea layers, we first extract n plus m different question representations, or instructions, with the instruction generators. So n for the NuTrea expansion step, and m for the backup step, which will be introduced shortly. Next, we initialize the node scores. The seed node scores are set to 1, and the rest are set to 0. Then the NuTrea layers propagate information outwards, starting from the seed node. Each NuTrea layer consists of 3 consecutive steps. The first step is the expansion step, which transmits information to adjacent nodes with respect to the expansion instructions. Here, if an incident edge type is similar to the instruction features, higher scores will be transmitted. The next step is the backup step, where def information is aggregated from the subtree. And similar to the expansion step, information relevant to the question context will be aggregated with the efficient max pooling operator. And in the figure, each node subtree with def2 will be pulled and scored based on the backup instructions. Finally, the node scores are computed by summing up the expansion and the backup scores and normalizing across nodes in the knowledge graph. This process is repeated for every NuTrea layer for nodes assigned with a score, after which the nodes will be retrieved based on the final scores. Our NuTrea was evaluated on 3 benchmarks, achieving the best performance on the Web Questions SP and Complex Web Questions dataset, while achieving the second best on the MetaQA dataset. And in terms of efficiency, NuTrea induces slightly more training and inference latency compared to the most recent baseline because of the additional backup step. However, this NuTrea's effective architecture reduces the number of training epochs, requiring far less training time overall. Relevant code for NuTrea is released in the following QR code. Thank you very much.